Okay. So
Hello everyone.
welcome back to IGCSE Maths,
IGCSE
Live.
ZNotes Live,
And
and
we're back here.
we're
My
back
name
here.
is
My
Devan,
name is
and I'm
Devan,
your
and
host
I'm
for
your
today's.
host for today's.
And here we have
And
Ivan.
here
He's
we
the
have
expert
Ivan.
for this episode.
He's the
So,
expert for this episode. So,
hello, Ivan.
hello
Please
Ivan.
introduce yourself.
Please introduce yourself.
Thank you, Devon.
Thank you, Devan.
For those of you who haven't seen the previous episodes, my name is Ivan.
My name is
I'm
Ivan.
a master student.
I'm a master student.
Just graduated from the University of Cambridge. And today we'll be talking about Algebra and Graphs 3. So we'll continue on from our previous sessions. And yes, so without further ado, let's get right into it. So today we'll be dealing with a few different topics. So linear programming is one of them, and then we'll be moving on to sequences and how to evaluate them. And I think the last topic we'll be dealing with is also finite differences and how to find kind of patterns and formulas for various patterns that we see and using finite difference method. So let's go through the key concepts. Okay, so linear programming. So linear programming is a very nice kind of geometric way of looking at kind of problems that you want to maximize, like kind of maximization, minimization problems. And so, as said here, a method to find the best solution when there are linear equations or inequalities. And so we'll see that in a problem when it comes up. But the general steps are to figure out the wanted region by shading the unwanted regions and figuring out what's left. And then from there, you might have a kind of expression that you want to minimize or maximize, and you can do that so long as it's within the region that you're considering. And so that's why you interpret the question as a y equals mx plus c and draw these straight line graphs. Is there anything more I should add there, or should we just wait until we get a problem, Devan?
Yeah, that's it.
Awesome. Okay. So sequences, these things are obviously very useful. You know, when you have arithmetic sequences, what these things are is, for example, we have an example here: 1, 3, 5, 7, 9, 11. These obviously increase by 2 each time, and this is an arithmetic sequence because it increases by a number every time. And so the general formula is you get the first term, and then you add, to figure out the nth term, you add n minus 1 times the difference. So in this case, if you want to find the third term in this sequence, you go 1 plus 3 minus 1, which is 2, times the common difference, which is 2. So 1 plus 4 is 5, etc. And that's very useful because when you're trying to figure out the next terms, obviously sometimes it can be a bit complicated, and so this gives you just a simple way of doing it. However, it's always important to know where these formulas come from because sometimes that's more useful than just applying it. Okay, and we also have geometric sequences. So these guys similar, but they multiply by a common number. So here we have 1, 2, 4, 8, 16. So these guys multiply by 2. The first term is 1, which is your 8, and the common ratio is r. And similar to what's happening in this arithmetic sequence, to find the nth term, you just go r to the n minus 1. It's kind of like instead of dividing, instead of adding, you're multiplying, and that's why you get a power instead of a multiplication right there. And so this is the common term we can figure out from there. There are also formulas to add these, and I guess we might be looking at these later, or does that not appear in general?
Oh, that one is not in IGCSE, but it'll be out at AS level. Yeah.
Okay, cool. So you can also figure out ways to sum these, and they're very useful in general, but don't worry about this. You'll only be asked to figure out what the terms are. And we'll see examples of this later, but in a different form. And so, yeah, now we continue with sequences. So when you're dealing with sequences that are made by polynomials, one way to kind of to analyze these guys is through finite differences. So here we have a polynomial generated sequence, 9, 20, 33, 48. And so you can do a finite difference. This means taking 20 minus 9, getting 11, 33 minus 13 and getting 5, etc., etc. And then doing that again and again and again. And so you might ask, when do you stop? Well, the time you stop is when you get to either all zeros or constants. Like in this example, we have 2. The next row will be 0, 0, etc. The point where it stops is the interesting point. So this is obviously the second difference, and it gets to 2. And this is actually telling you your polynomial is a quadratic polynomial. So this is why finite differences are very useful. So if you start with the quadratic polynomial here, when you take the finite differences, you're going to get a linear polynomial and then a constant. That's the idea. So every time you're decreasing the degree of the polynomial. And so when you end up at when you know that your polynomial is quadratic, then you have a general form, a squared plus bn plus c, and you can then find what a and b and c are. Because you have 3 unknowns, you'll need 3 equations, and so 9, 20, and 33 are natural equations to use. You can sub in 1, 2, and 3 in there, and you'll find what a, b, and c are, and now you have the formula for the sequence. So we'll see some of that later on. This is a very useful method, and in fact, I'll also show you a technique that will help you figure out the formula just from the finite difference table, rather than having to use a few linear equations. But granted, it is a bit more technical. So if you can do it. But if you can't, then this method is perfectly fine as well. Anything I should add, Devan?
Yeah. I think that's it for this topic. Yeah.
Okay. So now we've got a few problems, and let's get right into them so that we can start. So, as I mentioned, you're beginning some sort of inequality type questions, and so the question is, by shading unwanted regions of the grid above, find and label the region R which satisfies the following 4 inequalities. So the first inequality is y is greater than or equal to 2. So how to graphically write that is you graph the line y equals 2, and then you figure out which one would correspond to y is greater than or equal to 2. But in this case, because we're shading the unwanted regions, in this case will be y is smaller than or equal to 2. So we can figure what that is out. The line is this one, y equals 2, and smaller than that. So this is the region we're interested in. Now we have another line, x plus y is greater than or equal to 6. In this case, we'll be pointing not in the positive way, but in the negative way. And your y-intercept will be 6 for x plus y equals 6. And so x plus y is greater than 6 is what we're looking for. So we want the opposite to that, which is less than 6. So it's on this side of the line. We shade that in. For this one, y is smaller than or equal to 4. So in this case, your graph plus 4, it's going to be pointing this way. And its y-intercept will be 4. So it's this line right here. And we want y is less than that as our wanted region. So it's going to be above this line, as our unwanted region. So we get that. And then finally, we have x plus 2y equals 18. Again, because it'll be pointing this way. And it's x plus 2y is smaller than or equal to 18. So we need x plus 2y to be greater than or equal to 18. And in this case, it'll be on this side then, that line. And now we have our region that we know that we want, which is this little quadrilateral right here. And now you might be asked maybe a question. It might be, given these conditions, how would you maximize x plus, say, y on 3? Maximize that for me. What's the maximum value x plus y on 3 can attain? And to solve this, you can graph that line, x plus y on 3 equals 0, say. So this is the graph. I've put it right here. And now we have to figure out when this is maximized. So when you increase x plus y on 3, it goes this way. And so it's maximized when it meets this little extreme point right here, this vertex. And so you figure out the line that passes through here, and then you get your maximum value. So that's how you can kind of solve these kinds of questions. So you can figure this point out by intersecting y equals 2 with this line here, which is x plus y is equal to 18. Find the intersection, so y equals 2, that gives you x is x is 14. And then you'll be able to figure out what x plus y on 3 is and where that maximum is. In this case, y is 2, so 2/3 plus, we have x, so x is 14, so 2/3 plus 14. That'd be one way of doing it. What do you think, Devon? Does that sound, did I explain what we need to do?
Yeah, you explained actually a lot here. That's great.
Okay, cool. So this is a useful way of solving these types of problems. And in fact, it's useful in basic economics stuff when you have these kinds of lines and you want to maximize certain things like cost. Okay, so, and you can even do it in 3D or 4D depending on what you're going. But that becomes much harder. Okay.
You need a computer for that, usually.
Exactly. But we're in GCSE, so the questions won't be 3D. Okay, so these types of questions are very important, and this is our main focus for today. So we're given a kind of geometric situation, and we want to then determine a kind of formula for number of small lines and things like that. So there isn't really a general way to do this. Because it really depends on practicing and being able to notice what's increasing. So of course, when we look at from diagram 1 to 2, we're adding these little bits here on the sides. So one kind of thing I did was I started drawing lines like that, figure out what I'm adding. And this made it a bit easier because when you're looking at small lines, so we have to complete this table. We could obviously count for diagram 5, but what we're interested in is to figure out how we calculate diagram 6. So we have to find a general way what we're adding each time. And so what we notice is that we're adding 2 sets of these small lines, and then plus an extra one of these small lines there. So 2 times 2 accounts for this, plus 2. Same thing here, you have 2 times 3, these little extras, plus 2. So this is what we're adding each time for small lines. So we can calculate simply for our diagram 5, or we can use our formula. So the small lines, we're going to add 2 times 5, and then another 2. So in fact, it's like 2 times 5 plus 1. So 2 times 6. We get 40. So we add 2 times 6, which is 12, and add that 28. So, and then the next one will just be 2 times 7, so it's 54. And now the dots. So these dots, we can figure out also what's happening here. So it looks like the dots we're adding is this one and this one, and then these extra 2 right there. So these ones here, and also still an extra 2. So it seems like it's a very similar kind of way. We're adding 3 plus 2. 2 plus 2, and 4 plus 2. So we seem to be adding, so the next one we'll be adding 5 plus 2, which is 7. And the next one we'll be adding 6 plus 2, so we add 8 and we get 34. So as I said, there's no general way to do this, but if you look at what's added, then you can try to figure out how that relates to the diagram number, which in this case 453. So that's what I've done, and generally it should work like that, pretty simply. Now, the next question, which you can imagine what will happen, is we have to figure out a formula So given the sixth diagram, how do we know how many things we have after that? So how many small lines and how many dots for any diagram. And so these are contents of the next questions. So for diagram n, find an expression in terms of n, the number of small lines. So there are a few ways to go about this. Both of them rely on the finite differences. So we're going to calculate them. So we have our first line here, which is 4, 10, 18, 28. And then we take the finite differences of those guys, is the next line. And then again. Now, when you're doing the working out, I suggest you do probably more numbers, so you can get, because we have more, we have, I think, 34 and 54 or something like that, and to make sure that this line is constant. But we can clearly see it's going to be constant. Well, we think so anyway. As I said, when it's constant, this means that it's a quadratic polynomial. So we'll see later on how you could solve this question using this quadratic polynomial. You'll just have to sub in 3 values and find a(n) squared plus bn plus c, find a, b, and c, and you'll be done. Another way you could do this is guess. There's also this last way, which I like personally, but it's slightly more involved. And so what it entails is you have to find this 0th kind of diagram. So this is the first one, and this diagonal we call the first line. And so we want to find the 0th line. So we know that it's going to be 2's all along here. So to find that 0 line, we could just put a 2 there. We know this 6 minus 4 is 2, so the next one is 6 minus 2, which is 4. And this one is going to be 4 minus 4, which is 0. So kind of like backwards tracking. And now all we have to do is we take these values, so 2, and we multiply by n choose 2. So this thing you wouldn't have seen in IGCSE, but we'll explain it later on. 4 times n choose 1 and 0 times n choose 0. And you add them, and you get n squared plus 3n. It's the formula. So this is quite complicated. I know you haven't seen it in GCSE, and you don't have to do this method, but it's a nice way of being able to get the formula without doing much work, because the finite difference table gives you everything you need. And I'll explain you more how you get this, especially explaining this thing right here. This n choose 2 business is you go n times n minus 1 on 2 times 1. And this is going to be n on 1. It's going to be 1. N choose 0 is always 1. But if you guys know what that is already, congratulations, that's awesome. But if you don't worry about it. Okay, so now we're going to go with C. So C is diagram R has 10,300 small lines. Find the value of R. So we have our formula, which is n squared plus 3n. So r squared plus 3r is 10,300. And we want to then find the value of r that solves this. So we can then get a quadratic equation by taking it to the other side. So r squared plus 3r minus 10,300 is 0. We can then factor it. You could use a quadratic formula, but in this case, I found it pretty simple to just guess what the 2 numbers that multiply to that and add to 3 are, and it was pretty okay. It was 100 and 103, negative 103 and 100, and we get r equals 100 because obviously we're not looking for negative diagrams. And yeah, so we've done these quadratic equations for quite a while now, so I think we must be quite used to them. So let me just elaborate now more on this method here for those that are interested. It won't be long because it's quite complicated, but if you are interested, we can. I'll show you how that works. So if our polynomial was something like this, ak x to the k plus ak minus 1 x to the k minus 1 plus a naught, we can then set up a finite difference table. So the 0th one here is p of 0. The one here is p of 1. T1 is going to be the difference of p1 and p0. And the next one is going to be difference of P2 minus P1, and etc. We make our finite difference table. And so now, from our formulas, we know that to get this guy, T11, we take the guy above it, T10, and take away T00. So this is all this is saying right here. And so we can rearrange it to get this. We can isolate T and I, which is the guy on the nth column right here. And we solve it in terms of the previous two terms. And now what we do is we define a shift operator. So to get T10 from T11, what I do is I shift T11 to T00, and I add them, and that gives me this guy. And so what we get is something quite interesting. We have T and I is just T n I plus 1 plus the shift operator. And then when we use the binomial formula, expand all that stuff, we get something a bit crazy looking. But we get our formula. So the nth term is this. This is how we find our polynomial. We get n choose k times tkk plus that. And those are the guys on that 0th diagonal which I was talking about. Now, this choosing function, how you calculate is, if you got n choose k, you're doing n times n minus 1 times n minus 2, all the way for k terms here. And then you're going divided by k times k minus 1 times k minus 2, ... So n choose 3 would be n times n minus 1 times n minus 2 on 3 times 2 times 1. So make sure you have the same on the bottom and the top. But as I said, this is not that important, and for those who are interested in, you can message us more about it, but for those who aren't, we will now see how we can solve the question without this. So, our next question is, the number of dots in a diagram n is an squared plus bn plus 1. Find the values of a and b. So, what's useful about this part is they give you what the formula is. However, if you found a finite difference table and saw that it ended on the second difference, you would know it's a quadratic formula anyway. So, how do we solve this? Well, we have the number of dots. For n equals 1, the number of dots is 4, and for n equals 2, the number of dots is 8. We have two unknowns, a and b. So all we're going to do is, we're going to do our favorite method of solving linear equations. And as I mentioned, I think last week, that one is usually substitution. So the first equation tells us that b equals 3 minus a. And we substitute in the next equation, so put b equals 3 minus a, and you get 4a plus 6 minus 2a plus 1 equals 8. And therefore, a equals a half. And then solvingly, b equals 5 on 2. And so now, all you would do is, you're done. But because it's important to know that you're right, it's important in maths to be right, you can check whether this formula holds. And if it does, you can be quite confident that you've done it right. And so we could have done that for the previous question. However, I complicated because at least you don't have to then do linear equations because you have it all right there for you. But on the flip side, these linear equations are a bit easier and probably might give you more marks. So what's my suggestion? Do this way. But if you feel like battling with combinatorics, which you will do in A levels, then maybe you can give the other way a shot. Okay, well I think that's it, Devon. Anything else I should say?
Yeah, I think that's it. But in the first part of the question.
Yep. You want me to go back?
Okay. Yeah, please. By the way, is my voice choppy?
No, I think it's all good. Yeah.
Ah, okay. No, before that, at the very first part of it. It's not really that important. Oh no, before that, right? Exactly before this one.
The linear programming one, or?
Oh no.
This one.
Yeah, this one. It's not really that important, but you can get the answer for diagram 5 and 6 just by looking at the sequence itself. So for the number of small lines, we see that 4, 10, 18, 28. 4 to 10 is that you just have to plus 6, right? How do you go from 10 to 18? You just have to add 8. Going from 18 to 28 is just you add 10. So you see the pattern here is like plus 6, plus 8, plus 10. So what's next? You should plus 12. That's why you get 40 for the next diagram. And also for this 6 diagram, same method. Since it was plus 12, next should be plus 14. That means 40 plus 14 is 54. You can also do the same thing for the number of dots. So we have 4, 8, 13, 19. So we notice that from 4 to 8 is plus 4, then plus 5, plus 6. So what's next after 6? It's 7. So 19 plus 7 is 26. Then what's after 7? 8. So 26 plus 8 is 34. So that's another method you can do to answer the question. It's worth 4 marks.
Yeah, exactly. So as Devon pointed out, for this question, that'll be the easiest way. Of course, one of the things is that sometimes you can get cubic or quartic formulas, in which case the difference is not obvious. And so this is why I tried to show you, a kind of a way of doing it, but differently. But yeah, as Devon said, that is the easiest way in this question. So if you can see that pattern immediately, just go for it. Everything okay?
Yeah, sorry, I was having connection problems. And
No.
I think that's it.
Awesome.
Okay.
So I guess that's...
So we can
Is that it? Yeah.
we can head to the thank you page, yeah.
Okay, let's head to the thank you.
So yeah, thank you everyone for watching with us today, and thank you Ivan for teaching our friends. So don't forget, we'll have another episode on Friday, and don't forget to check out our Instagram page, website, or even our Discord server. So yeah, that's it for today. Thank you, and we'll see you again.
Thank you, everyone. See you next
Thank
week.
you.